Okay, so from last time, we were talking about infinite limits, right? So this kind of feeds into another idea. So how do we know if a function is undefined for a certain number? Because it causes us to divide by 0, right? When we try to evaluate directly. How do we know whether the function has a whole or an asymptote? Okay, so that's usually what people defer to. They'd say if it's a number divided by 0, that's obviously a vertical asymptote, right? If it's indeterminate, if it's 0 over 0, the examples we've always looked at turns out to be a whole, right? We could fill in, it was a whole, and by resolving the indeterminacy, we ended up filling in the hole in order to answer the question, where does the ant think he's going to step, right? Okay. That's not generally true. You can't make that assumption. Okay, we often assume that as the limit approaches C, if it's indeterminate, it must correspond to a whole, but that is not true. If it's indeterminate, it truly is indeterminate. It could still resolve to either, remember there are three kinds of limits when we evaluate, three kinds of results that we could get when we try to evaluate directly. First one was we get an answer, right? We get an answer and that's our limit. Second one was we get a non-zero number divided by 0, which was, does not exist, which means it's an asymptote, okay? The third one was the one that required more work. That was the one where we had to do something, and we did a lot of practice on that, right? We had the cancellation technique where we factored polynomials and canceled factors. We did some examples where we had complex fractions, right? Some with the rationalizing technique where we had to multiply by the conjugate, top and bottom by the conjugate of the expression that had a square root in it. All those were dealing with that third type where we had to do more work. Okay, what's ultimately going to happen if it's indeterminate is eventually it's going to turn into either a type 1 or a type 2 once we resolve the indeterminacy. It doesn't always turn into the first type. It could end up actually being one that's a vertical asymptote. You just don't know until you find out. Okay, so after removing the indeterminacy, if direct substitution yields a numerical answer, then it's a whole, right? Then it's a whole. Then what did we do? We traded the function that had a whole for one that didn't, and so it made it easy to answer the limit question. Where does the ant think he's going to step? Well, he's going to step on the location of that hole, which in our new function where we fill in the hole, we just evaluate that, right? Okay, that was our trick. But after removing the indeterminacy, if direct substitution gives us an answer of the form a divided by 0, where a is non-zero, then that's a vertical asymptote. Could be either one. Okay? Like what about this guy, for example? If I try to take this limit as x approaches 2, call this f of x. If the limit of x squared minus 4x plus 4 over x minus 2 as x approaches 2, if I try to evaluate directly, what do I get? Indeterminate, 0 over 0, right? So what would I do? Factor the top. So that just factors into x minus 2 times x minus 2, right? What's that simplify to? Okay. Which is 0. Okay. So that one had a hole. That one had a hole at the point x equals 2, y equals 0. Okay. And that's the limit. Okay, how about this guy? almost the same stuff, right? If I factor bottom this time, cancel the factors, and so I get the limit of 1 over x minus 2 as x approaches to, that's 1 over 0, right? So that doesn't exist, and what's that tell us? Vertical asymptote. Okay, so it could be either way. Both of those started off indeterminate. Okay? Okay, what would we do here to locate any vertical asymptotes or holes? We certainly could. Yeah. We may not have to. Maybe we do. Say it again. Yeah, in fact, we don't even really need to find the zeros of the top at first, right? Because think about this now. If I'm just trying to find vertical asymptotes or holes, what does that tell you about the denominator when I evaluate directly? It's got to be 0, doesn't it? Right? If it's either going to be indeterminate, 0 over 0, which means it could be either 1, or what's the other alternative when I evaluate directly? At what value? What's going to be the value we want to take a limit at, potentially? At 1, right? Okay, good. When I take a limit at as x approaches 1, the bottom is 0, for sure. What if the top is not 0? Then it's a vertical asymptote, isn't it? Right? Then that would be a kind where I end up with a number divided by 0, a non-zero number divided by 0, which would tell me it's a vertical asymptote. So do I need to jump right in and try to do a bunch of fancy algebra here? Maybe not, right? I could just evaluate this limit at 1 first to just see what happens, right? So if we do that, we're going to find all the values of x that are zeros of the denominator. And then if we end up with some number over 0, it's a vertical asymptote, end of story. If it's indeterminate, we got to do something. And then we have to do more work and see which one it is. What do we get here? And then in that case, that it's indeterminate, if that resolves to a numerical answer, it's a hole. And again, if we get a number divided by 0, it's a vertical asymptote. So what happens here? What is, if we try to take this limit, if I try to evaluate that directly, what do I get? Do I? Oh, I do, don't I? I do get 0 over 0. Unfortunately, I do. I was kind of hoping it wasn't one of those. It's 0 over 0, so I would have to resolve this indeterminacy. Okay, but what if it weren't? What if that was like a plus 13 or something under the radical? Then I wouldn't have to do any fancy math. I would just be done. I would know I get a number divided by 0, and so it's a vertical asymptote. Okay, make sense? I'm not going to go through the whole process of doing that, but we would have to, this is one where we would have to use that rationalizing technique, okay, that we spent a lot of time on previously. So let's go back to this problem that I posed to you at the very beginning of the year, which kind of inspired our journey into our investigation of limits, right? So science fiction writers often imagine spaceships that can travel to far-off planets and distant galaxies. However, we've got some problems here, right? Because Einstein showed us, this is back in, it actually wasn't 1905, it was after that. That was special relativity, but close to 1905. Relativistic mass is equal to rest mass, in other words, the mass of an object when it's completely at rest, divided by the gamma factor, the square root of 1 minus v squared over c squared, where v is the velocity of the object and c is the speed of light. Okay? So why is this a problem, traveling the speed of light? Light has no mass. You're right, it has no rest mass. It has momentum, which is crazy. It actually has relativistic mass. It just doesn't have rest mass. But go and tell me more. I want you to use math to give me something akin to a proof here. Why is it that objects with mass can't go the speed of light?
Because the speed of light is measured no mass.
Okay, these are all abstract, kind of conceptual answers. I want something concrete.
When something is heavy, like somebody that's lighter can like move faster than somebody that, like if something's thrown through the air, something that's lighter, for example, light can move faster than something that's heavier, which is everything that has mass.
Okay, again,
V squared with C squared?
say it again.
The V squared with C squared?
Has something to do with that, doesn't it? Yeah, so in order for us to go the speed of light, what would have to happen here? Your velocity would have to be,
The speed of light.
c. V would have to equal c, right? Okay, well what happens if I let v equal c?
Oh, then
Then
it's
you get 1
indeterminate.
minus 1, which is
Oh,
zero,
it's-
0, 0.
I get 0 on the bottom, don't I? Yeah, not on the top. I get a 0 on the bottom. The top is just some constant, whatever the rest mass is, right? So this function is undefined. If this is m as a function of v, let's say, and that's really what it is. It's relativistic mass as a function of velocity. It's undefined at v equals c. But go further. It's undefined there, but what could we do now to try to explore what its value is?
If you get really,
Okay, what do we, yeah, that sounds an awful lot like something we've spent some time on. Okay, it might end up being an asymptote. How do we get there? What are we doing? We're finding a limit. Yeah, we're taking a limit of this, right? As v approaches c, and specifically in this case, it approaches c from which direction? From the left. We have to approach c from values less than c, right? Does that make sense? Okay, so then what happens if we explore that limit? The limit of rest mass divided by the square root of 1 minus v squared over c squared as v approaches c from the left is what? I get m naught on the top. What do I get on the bottom? Square root of, yeah, I'm going to get the square root of 1 minus v squared over c squared. I could just call that v over c quantity squared, couldn't I? Everybody agree? Okay, what's v over c? What's that ratio going to approach as v approaches c from the left? Gets really close to 1. Yeah, it's going to be slightly bigger or slightly less than 1?
Slightly less.
Yeah, so I'm going to get 1 minus 1 minus. 1 subtract 1 minus. What does that look like?
0 minus.
0 minus?
0 plus.
0 plus. Because this is what 1 minus is going to be something like 0.999, right? 1 minus 0.999 is going to give me a really small positive number. Agreed? So this looks like m naught over the square root of 0 plus. Well, what's the square root of 0 plus? 0 plus, right? It's just a small positive number. Okay, well, dividing by 0 tells us what? If I've got a non-zero number on the top, say it again? Okay, and that's exploding towards, it's going to be an infinity, right? It's exploding. And what's the sign going to be?
Positive.
Positive.
You have to have a positive mass.
Yeah, mass is positive, right? So there's the problem, right? there's the problem. In order for an object to approach the speed of light, it would require an infinite amount of mass. It would require an infinite amount of mass, right, if it were going to approach the speed of light. And that would mean it takes an infinite amount of energy to accelerate that, and that's not available, right? So can't work. I told you guys the story about the electron or the positron at Stanford. Okay,
I feel like you might.
I think maybe a couple of years ago, maybe. So it's, I mean, just to illustrate this, like the Stanford Linear Accelerator, 3-mile-long building, all it does is just accelerate subatomic particles, you know, using this massive array of klystrons, these superconducting magnets. And you can invest in an equivalent energy to the entire energy usage of the rest of the Bay Area. You can invest in this one little packet of positrons, you know, anti-electrons. And even then, you know, it doesn't go, they don't go the speed of light. They just go 99.999999997% the speed of light. Because as those subatomic particles get pushed closer to the speed of light, their mass continues to increase. And so they just require more and more energy to push that velocity higher, right? You can never get to C. It just can't happen. Okay, make sense? All right, so we resolved that. That's good. We know what's going on.